See, this resin itself is flexible. It's a flexible type of resin, and it's also produced very thin, so you can produce some parts with very interesting properties using SLA. And this has been a different kind of resin that's more solid. It's a bit stronger, more resilient to impact, right? It's not flexible or soft. You can hit it with a hammer and you can take the shock and impact of that. See, so over here, what they're showing in the video is, if I can go back one frame, this part has been produced through stereolithography, so you can sort of see that the surface is quite smooth, whereas this part over here has been produced using fused deposition modeling. So what we previously discussed, yeah, with melted filament. And you can see the surface finish is not of the same grade. That's one of the main differences, or why you would select stereolithography over fused deposition modeling. But again, there are some disadvantages of SLA which would lead you to choose fused deposition modeling over SLA, such as always having the need to post-process your parts in SLA. Sometimes in fused deposition modeling, you don't need to post-process your parts, right? If you're happy with the surface finish, or if you want just a quick rough part to be produced, you can do that. With SLA, you still need to rinse off all of the excess resin and whatnot. And also, SLA produced parts that are prone to UV degradation. So if you wanted to put your SLA parts in direct sunlight, they will change color, they will become brittle, they will actually degrade over time because of that, those UV rays present in sunlight. Whereas in FDM, thermoplastic filament, it's more sensitive to heat, right? Because you use heat to melt it. So if you live in a hot country and you produce something using PLA, right? So not ABS in FDM, but PLA in FDM, that, you know, melts at a lower temperature. Some can even melt at 180 degrees Celsius, right? And I'm not saying that in hot countries temperatures can reach 180 degrees, but if you say leave one of these PLA produced parts in your car, so as an example, you want to produce a phone holder for your car using 3D printing, you can. But if you use PLA material and live, let's say, in a hot country such as in the Middle East, yeah, where temperatures can reach in excess of 30 degrees outside, in your car they can reach, you know, very, very high temperatures, not 180 degrees, but enough to actually affect your parts, to thermally degrade them, such as make them weaker over time, change their color over time and whatnot. But it's not the sunlight itself that affects these parts. So if you live in, let's say, like a colder country, or a country where the temperature is more consistent, such as in the United Kingdom, if you produce these parts for, you know, for your car, the interior of your car, the same phone holder, that will be more resistant. But if you produce a phone holder from using SLA, yeah, from resin, you would not be able to produce this phone holder for your car, because sunlight will keep penetrating inside your car and affecting this part. So that's just something to keep in mind, something to be aware of. Yeah. Here, what they did is they produced this using FDM, using thermal filament. So they just showed how weak the layer lines are. So how weak the bonds are between the layers of the 3D printed model. It's quick to snap, because obviously you print one layer, and then before you come and print the next one, this layer has already cooled partially. When you deposit the next layer on top, they don't fuse together 100%, they only partially fuse together. So that introduces some level of weakness along the build direction. Whereas SLA produced parts, because it's a chemical reaction the resin has with the UV, yeah, it's not melting, it's actually chemically hardening each layer on top of the next. They fuse much better. So as you can see, it doesn't snap as much of, as dramatically as the FDM produced part. But it also snaps. They're also relatively weak as compared to selective laser sintering and selective laser melting, which actually use metal, and they also form much better bonds. So this is the build plate rising and pulling the model out of the resin bath. So yeah, that's stereolithography. Let's see if we can get something out of the second video as well. So you can see this is not the actual printing speed. This is a sped up version of it. It's more of a time lapse. It's not, unfortunately, it's not as fast as in this video. This is a sped up version because otherwise the video would be 30 minutes, maybe 1 hour if it showed the whole process in actual real-time speed. Because obviously it cures it with the UV laser, but then it needs to accurately move it out to prepare the next layer. It needs to wait a bit before using the laser again, and the laser needs to shine for a set amount of time into the resin for it to harden, right? It can't just briefly flash onto the resin. It's a very, let's say, controlled, or it needs to be an accurate process. How long the laser needs to be shined on a particular area in order for the resin to harden. And there are differences between each type of resin that you obtain. You can sort of change all of these parameters within the machine. Obviously, each machine is different and they have different powers of lasers. So there are many many differences between machines, between material, between manufacturers that you can play around with and tweak in order to get, best built parts or the best effect or the best manufacturing process. Obviously, some manufacturers of machines. So when you buy SLA machines, they give you an instruction manual. They give you some recommended settings. They give you some recommended materials or material suppliers to obtain, the resins from. Some resin suppliers, they also give you some parameters to use with their resin, but experimentation is key in this part. Playing around, tweaking some of the parameters, some of the factors can help produce better parts, but this comes with, with many hours of experience using these technologies. Some stereolithography machines, they have a little roller, or let's say arm, that goes across the surface in between layer to smooth out, to remove air bubbles in the resin, to smooth the surface, to produce better parts as well. Some resin machines, you pour the resin, as we saw in the previous video. Some resin machines, they have cartridges of resin. So it's similar to an inkjet printer where you change out the ink cartridges, you add the new cartridge. You can do the same with this stereolithography machine, right? You can insert a cartridge of resin if you don't want to, pour it or handle the resin yourself. But these tend to be a bit more expensive. Also, some technologies or SLA machines, they also shake the resin bath a bit to get rid of these bubbles that are inside, because you don't want to, have a bubble in between your build plate and the glass, yeah, where the laser shines, because if a laser shines on this bubble, it won't harden it, right? Might harden the surface around the bubble, but it will be an imperfection in your model, and it can look bad. It can produce a rough surface finish, and it can also make your model weak. So bubbles are not good in this situation. This is how the laser actually shines through, and you have some mirrors that actually reflect and direct the laser to shine it at the specific areas that need to be hardened. And that was the, if I go back a bit, that's the transparent windows over here. So that's the bottom of the resin tank up here, that one, right? So this is the bottom of the resin tank, and the laser lies underneath that. And this is, you can see this bubble being over here, that could actually produce an imperfection onto this surface over here of the model or of the support structure, which is not ideal, but that's the laser sort of tracing and hardening the cross section of the model. So as you can see, the printed part will always be upside down, and just because the build plate, this would be, let's say, the bottom of the part that you're building, and we'll pull it up. Again, you can see the support structures supporting each layer, because if you wanted to, let's say, harden this area over here and you didn't have support structures, it would just fall down over here and stay in the resin bath. Whereas here it can be attached to the build plate using the support structure. So this is an element of design that needs to be considered when using this technology. So you can see that most elements designed, or most models, tend to have these support structures included. So generally, obviously, in most cases, because you still need an element of post-processing because of rinsing these parts, they tend to also add support structures because there's a post-processing step involved. Might as well go all the way and add these features because you'll be removing them at the end anyways. So yeah, that's been stereolithography. So let's move on to the last technology, which is laminate object manufacturing. And this is the one where you have laminate sheets that are cut layer by layer with a laser. Okay? This one is not as prevalent or common in the additive manufacturing environment. The main ones are FDM and SLA for hobbyists or enthusiasts, yeah, and professional versions of this, which are used in industry as well to produce models and user parts or casting molds and whatnot. Selective laser melting sintering that's not available to hobbyists or consumers just because of the price of these parts. They're several $1,000s. The equipment and the material itself is also expensive, this powdered material, but they are very prevalent in industrial applications. Laminate object manufacturing, again, because of the bulk of the equipment, is not generally found in many hobbyist environments or consumer environments. It's mostly in an industrial application, but also because of the limited applicability, there's limited industrial applications where this is used. Now, let's see if we can find a little video over here. Here they list it as layer laminated manufacturing, or it's just a different way to say laminate object manufacturing, but it's all the same. So you can see this would be quite a bulky unit, because you need to store the layer rolls, the feed spool and waste spool, and as you will see, each layer has to be traced out. So you trace out the box for the layer just to remove it from the laminate roll, and that stays over there, so it encapsulate the whole part in a block of material. You'll see that in this video. So over here, obviously the feed roll and the waste roll, they're in this cabinet underneath. You won't see them, you just see the workspace over here, and you see the layer or the sheet present in the workspace to be worked upon. Right now what's going on, you might not see it, but there's a laser here which is actually cutting the cross-sectional area and the box from the laminate sheet. And then it goes down, and as you can see, it traced a little square encapsulating area for this layer. As it moves on to the next layer, it moves the build plate down one layer, rolls a fresh layer of the sheet, moves a heated roller on top to melt this new layer on top of the old layer, and now with the laser it will trace the new cross-sectional area, cutting it onto this second layer. And it keeps going back and forth until all the layers are complete. Okay, now that we can see sort of how behind the scenes, like behind the cupboard, you can see the feed roll, you can see the waste roll, you can see how each layer a square is cut because it has to bond it to the previous layer, so it helps with removing the part or the model from the whole block, because obviously the heated roller bonds each layer to the next, or each sheet of laminate material to the previous sheet of laminate material. And it cuts, obviously it always cuts the same cross-sectional area of the block because it's melted on top of the previous one, so to be able to move the layers down. Again, as per most models, it has 2 degrees of freedom over here on the laser, the back and forth and towards us and away from us sort of movement, so the X and the Y. The Z again is produced by the build plate moving down. These lines, it hashes, it creates a grid around, so this is over here in the center, that's the cross section of the part per layer that we want, and this cube or grid around it, it's sort of splitting the surrounding area, in the layer to be able to be removed more easily. Obviously, it cannot create, it cannot just cut the layer itself. It needs to cut the whole block, because if you imagine, let's say, you're creating, as an example in geometry, like an upside down pyramid, because each layer the cross-sectional area is larger than the previous layer, this would jam the machine. It wouldn't be able to actually pull the layer down. So using this method of actually cutting out the whole rectangle, yeah, to create a block, this allows us to create more range or gives us more freedom of geometry. Although post-processing will be it will be a lot more difficult. You'll see once all the layers have been completed, you'll see how we can actually remove it. So obviously you don't generally see the feed and the waste rolls, you just see the workspace environment. There we go. So over here, this is the block that contains our model that's produced at the end. And as you can see, because you cut a grid, it's easier to remove all of the excess material and remove your model out at the end. But because obviously the cube that contains your model has to be relatively large in laminate object manufacturing, this can lead to a lot of post-processing and difficult post-processing because you have to remove all of the surrounding not needed, let's say, material that's not part of the our end model. And then obviously we can remove our model and then trim away all the excess material as well from our model. Until we end up with our finished model. So obviously laminate object manufacturing is not as commonly used as the other additive manufacturing technologies, but it also has its, its purpose. It's used in certain industries such as the architectural industries where they produce models of buildings or models of cities in city planning environments. Can produce this much faster than the more traditional method, which is done by hand crafting style of producing these models. So this can sort of minimize the amount of human time that's needed to actually produce these models, right? And generally you need a very experienced architect to produce these models, right? Whereas here you can design them in 3D rather than, physically sculpting them. So there's less of that artistic skill needed or technical skill to produce the models. You just need CAD familiarity or CAD software familiarity, which actually can be learned much faster and requires much less practice to produce such nice components. Yeah, and to actually remove the components from the laminate object manufacturing, the block, yeah, that's much less skilled labor. Yeah, pretty much anyone can learn how to do that relatively easily. So applications of laminate object manufacturing. But pretty much this was just to give you some additional content to the main base content that we discussed here in week 4 or in lesson 4. This is just to give you some, additional visual aids or visual guides. Obviously, you can Google each one of these technologies and you can find loads of resources on them, such as images, videos. You can even go on YouTube and search these technologies and you'll find loads of different videos showing you examples of how they work or what people produced using this technology. You can even find tips and tricks for when using these technologies, more so For FDM and SLA, you can find product or machine reviews for each of these technologies. You can find loads of resources just by doing a web search and Googling different things. So Google is going to be your friend in this environment. So that's pretty much it for this additional content. Thank you very much.